Next up, we have Rao telling us about one of two projects in this session connected to WebAssembly.
All right. Thanks for the introduction. And good afternoon, everyone. My name is Rao, and I am a PhD student from Imperial College London. Today, I'll be presenting our work titled Iris-Wasm, which aims to achieve robust and modular verification of real-world WebAssembly programs based on the method of building a program logic for WebAssembly. So for some background, let's first get on board with what WebAssembly is and how the language works in general. WebAssembly, which is oftentimes abbreviated as WASM, is a modern binary format supported by... You're a little quiet. Move the mic a bit. Sure, thank you. Testing? This one is working. All right, so let me get back on the previous sentence. WebAssembly, which is oftentimes abbreviated as WASM, is a modern binary format supported by all the major browsers. It is originally designed to be a compilation target for other programming languages such as C++ or Rust to run on the web efficiently. But now it is also possible to directly assemble WASM modules from string expressions using the WASM binary toolkit. WASM is rather special in having started from a formal specification, which has intrigued a lot of research on verification and security. So we describe the execution of WASM modules now in a bit more detail. WASM programs are distributed in the units of module binaries. To execute a WASM module after compiling it, the module first needs to be instantiated, for example, in the JavaScript API, where instantiating a module means basically having the defined state in the module initialized and allocated into the WASM runtime global store. The execution can then proceed with invoking the start function of the module if the module chooses to define one. In general, one WASM program may involve multiple modules, and different modules are allowed to share a part of their internal states across modules via an import and export system defined in WASM explicitly. So to sum up, the key part of WASM runtime semantics includes mainly a small step operational semantics, which describes the runtime behavior of the core WASM execution, and followed by a large and complex definition of module instantiation operation that describes the effect of instantiating a module on the WASM global store. This then brings naturally to the motivation of our work, which is to validate the key security properties of WASM definitions and to capture the intended behavior of these definitions in a compositional way, so that our verification model can be used to verify about real-world WASM programs. However, to build a model that is capable of such, we need to overcome additional challenges revolving around the interaction of WASM and its surrounding environment, instead of just dealing with the core small step semantics of WASM itself. And the reason that this is the case is because WASM execution is less idealized than a straight line of module instantiations and executions. In the most general setting, arbitrary interoperation between WASM and host is possible via invoking functions from one language to another. And in particular, the host can provide functions for WASM code to invoke, and these host functions can do a vast number of things, such as making re-entrant call to other WASM functions, or instantiating additional WASM modules, or even basically do anything else within the capability of the host. Some previous attempts of WASM validation and verification efforts have been made. For example, the WASM cert project, which includes two mechanizations of WASM 1.0 definitions in the Koch and Isabelle theorem prover, with the soundness result for type system and its module instantiation stated and proved. A program logic was then developed based on the Isabelle mechanization. However, that particular design was for a first-order subset of WASM 1.0 standard, and it is limited to a single module without imports or exports. Neither does it deal with module instantiation or any host interaction at all. And this leads us to our work, Iris-Wasm, where we have not only built a higher order program logic for the full WASM 1.0 standard using the using the Iris framework in the Coq theorem pivot, but we have also designed additional development to make it possible to verify real-world WASM programs with the presence of a host environment. So to be more precise on what these additional designs are, in addition to the higher order program logic for the full WASM 1.0 runtime semantics, our work also allows the reasoning about interaction between WASM and the host, which includes the general interoperation between the two languages and the instantiation process of WASM modules. Furthermore, we extended the reach of our reasoning capability to robust safety verification, where we can prove certain module encapsulation properties of a non-module with interactions with unknown module code. Lastly, to demonstrate the expressiveness of our higher order verification framework, we have developed an example of a stack module with higher order functions and applied our verification model to that stack module under several different settings. So let's get to the core part of our work a bit. Our program logic is based on Iris, which is a higher order separation logic framework that can be used to build programs logic for any given small step semantics of a programming language. And the key part of this process is to define a memory model in Iris for the program state, which means basically to describe the states of program using abstract separation logic assertions, where each assertion then captures the set of all states that satisfy this assertion. This general approach of using separation logic assertions is crucial for us to achieve compositional reasoning, and this is a general method that can be applied to any other languages instead of just WASM itself. For WASM in particular, because the WASM runtime store contains so many different types of objects in general, we defined a series of abstract assertions in Iris for each of the different components of the concrete WASM runtime state. And having defined all of those resource assertions, we can then proceed to build the core part of our program logic, which is the set of proof rules for the language. We prove, in general, one or multiple proof rules corresponding to each reduction relation defined in the small step semantics of WASM, which effectively captures the effect of execution on the program state by using abstract predicates for the state instead of talking about the full concrete state for the WASM store. And this is the approach that allows us to reason about the core execution semantics of WASM configuration in a compositional way. However, remember that we have only been talking about the core WASM instruction set so far. And in general, we want to build a model that can be used to verify real-world WASM programs starting from compiled modules with interaction of the host. One particular difficulty, as we have previously mentioned, is the interoperation between WASM and host, which can invoke each other arbitrarily. One naive solution at that is to view WASM and a particular host as one language itself with an intertwined and mutually recursive small step semantics, and then build a program logic for that combined semantics. But obviously, this approach has a severe limitation that it ties our model to one specific host for WASM instead of being a general solution. So what we do instead is to let host invocations result in an auxiliary stuck value in WASM, which can only be unstuck by the host language. An important design choice is then to make the WASM program logic parametric on the host logic instead of a concrete one. And all of this is possible because now the unblocking of the host calls are completely the responsibility of the host language now. And naturally, some additional proof rules are then required to connect between the WASM and the parametrized host logic. As a result of this design choice, a derivation of a general specification now, a general specification involving a reentrant WASM call now can bounce between the two logics for many, many steps indefinitely. Having dealt with interoperation between WASM and host, the last missing piece to achieve full modular reasoning for WASM programs is to handle module instantiation. And this is where we face a somewhat similar issue, because module instantiation is defined to be an operation of the host, and similarly, we do not want to tie our logic to a particular host. Our method here is to prove a host-agnostic lemma, capturing the effect of the module instantiation on the WASM part of the state itself. And to demonstrate how this works, we have also defined a simple host language which captures a bare-bone version of the JavaScript API, and we have built its associated program logic in Iris as well. In particular, we have proved the host-specific instantiation proof rule using the general version of that lemma. So with this done, what we have done so far has allowed us to fully reason about WASM programs where we know all the code of the modules we interact with. But however, even that is not the most general case, because in reality, we might only know the code of one particular module, which has certain import requirements, but we may not know the code of those imports directly. So to address this setting as well, we further extend our work to allow the verification of robust safety specifications, where certain encapsulation of properties of WASM modules can be proved during the interaction with unknown codes. This methodology is based on defining a logical relation on top of the program logic for semantic interpretation of the WASM type system, following by utilizing the strong typing guarantee of WASM modules. But however, due to time constraint, we cannot go into the details here. And this is a place where we invite anyone interested to read further into the paper. Lastly, to demonstrate the expressiveness of our work, we have developed a stack module that provides the allocations of new stacks and various higher-order functions for different stack operations, including a map function, which maps the entire stack by an arbitrary input function from the WASM function store. We have proved the instantiation specification of that stack module within our framework. To show what kind of verification result we can provide, we have applied our framework to the stack module under two different settings. In the first case, where a specification of the input function will be automatically provided, we are able to prove a modular specification of the map function invocation, which is parameterized on the specification of the input function naturally, demonstrating the high-order expressiveness of our logic. And in the second setting, where we would not know the specification of the input function even eventually, we are still able to prove the preservation of certain specific stack invariants, such as the length of the map such as the length of the stack after invoking the map functions under certain constraints. So to give a summary of the talk so far, we have presented our Iris-Wasm verification framework, which is able to achieve robust and modular verification for real-world WASM programs. And at last, I'd like to thank my wonderful collaborators of this work. And four of us, including myself, Maxime, Conrad, and John, are actually present in this conference. So feel free to approach us if you'd like to ask any questions to us. And this concludes my talk today. Thank you for your attention from the live audience, and also thank you for tuning in from the virtual participants. I'll be taking questions now.
Okay, our mic over here is open for audience questions. If anyone would like to take a shot at it. I can kick us off with one, which is that you were describing the modular specification of the stack module, and you talked about a WASM function table, which sounds like something a little unmodular. How do you make it pleasant to share that table across different clients? And what does that look like from a specification perspective?
Yeah, thanks for that question. So the WASM dynamic calls are indeed the most complicated part of the dealing with the control flow, because what happens in WebAssembly is that the WASM function tables basically contain indices to the particular addresses of the WASM store, which is basically a shared object across all the modules. And we are modeling both the table indices and the function indices as resources in our logic. And after that, we can basically include those resources in the precondition of the relevant proof rules for our reasoning process. And since that we are using a separate logic, then there's no further problem in dealing with this in the modular approach.
Would a realistic WASM program have anything like a dynamic allocator for the function table?
Well, So dynamically changing the table is not part of WASM 1.0 standard, but it is actually part of the 2.0 standard. So this is something that we might be looking to when we, if we want to update the standard to the more 2.0 standard. What we have done in the paper, though, is to still try to discuss this behavior because it is certainly very interesting. So, but WASM 1.0 does not have this behavior. So instead, what we have done is we added this table modification operation into our defined host logic, and then we stated and proved several examples reasoning with the presence of such a host function that can mutate tables, which is actually the more complicated part of the work indeed.
Got it. Thanks. Let's see. This is close to the last chance for questions from the audience. No burning questions? Okay. Well, then I guess we can make up a little more time and thank the speaker again.